the centroid again. Okay, so this is the centroid of interest. So now the perpendicular distance is to the what? Is to the element. Okay. Now the perpendicular distance is to the element. So therefore, this will be equal to plus, right? 3.441 times 10 to the power 3, and then multiply by 8. This is so bad. Then you multiply by 8. Okay, so the whole thing will be equal to 0. So finally, you have your mz or mh now will be equal to what? So minus 4.915 power 3 times 8 plus by 3.441 power 3 times 8 is equal to minus. Okay, it's good thing that we see minus. So minus 4.915 power 3 times 8 plus by 3.441 power 3 times 8 is equal to minus 11.792 times 10 to the power 3 pound inch. Now, minus means what? This direction that will assume positive shear is what? It's wrong. Okay, so from here, when it's minus, you have to bring it down. So when that's the case, you have to bring it. Wait, let me see. Did I do it correctly? Minus coming down is clockwise, anti-clockwise, minus plus 3.441 multiplied by. Yep, it's correct. So when that's the case, this will be equal to 11.792 times 10 to the power 3 pound inch, and then the positive direction is coming down this way. When it's coming down means over here, due to the bending is compression. Up here is what? It's tensile. Okay. Now, why the change is because, right? Why the flip is because at position G, okay, the previous position, we have 16. Now the 3.441 times 10 to the power 3 is only 8. Okay, so minus 4.915 multiplied by 3 times 8 plus by 3.441 power 3 times 8, you have a minus 11.792 times 10 to the power 3. Okay, so this is how you deal with what? Combined loading. And the unique thing about this is both our forces, our force component AZ, AX, and AY generate a moment about the x-axis. Okay. Now let's do another example. Okay, let's deal with another example. Okay, I'm going to pick another example. Okay, we're going to do this one. And we're going to follow the exact same procedure. Okay, and you will watch that the procedure did not change. Okay. And I want you all to see that the procedure did not change. This is really, really important. Right. So this is our example number 2. So what we have is member AB has a uniform rectangular cross section 10 by 24, as you can see over here. For the load shown, determine the normal and shearing stress at point H and point K. We're just going to focus on the normal stress. I've not taught you guys on shearing stress yet. Okay, shearing stress will occur the week before the term test. Okay, all right. When we have problem like this, right? It's best that one of the axes is or the transformation. Remember, we have this transformation, right? Right. Remember, we always said this transformation x, y, and we have rotation about z. Okay. Now, this transformation is not always okay. It's still based on right hand rule, but it's not always x has to be horizontal, y has to be vertical. Okay, not always the case. Okay, the best practice, okay, for doing this is the first thing we draw. We are going to sketch the centroid of interest. Okay, we're going to sketch. So the element H and K is where we want to find the stress. So the centroid, okay, that is relative to the element is this. This is the centroid relative to the element, right? Okay. So now this is our centroid. Okay. So this is our centroid. Okay. So this is our centroid. Relative to our element H and K, right? So when this is the case, now we can call this our x-axis. Perpendicular to it is our y, and this is our rotation about z. It makes your life and my life easier. Okay, you can deal with this transformation, but good luck. Okay, you are going to make mistake somehow or the other later on. Okay, so when you have this, when you have done this already, right? We look at our components now, right? So we know that we are going to have our right. This is our gx, and over here this is our gy, right? And from here we know that this is our 30 degrees. Okay, we know that this is 30 degrees because it's given. Okay, so immediately you can write this down that gx will be equal to 9 times 10 to the power 3 multiplied by cos 30. Okay, so 9 power 3. So it's equal to 7.794 Newton. And then we know that we have our gy will be equal to 9 times 10 to the power 3. And then we're going to have sine 30. Okay, so sine 30, that's a 9 power 3, is equal to 4.5. Okay, it's 9. Okay, so once you draw this, right, now you can rotate, right? You can rotate your entire element. Sorry, you can rotate your structure now such that it's easier to visualize. Okay, but before 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 we do that, right? We are aware that there are components in both A and B. Okay, so if we were to sketch our free body diagram, okay, we are going to sketch our free body diagram. we know that over here, this is our by, or it's not our by. I'll call this our bx prime or by prime. Hold on, let me see. If I were, yeah. So if I would now call this axis that I'm going to sketch down here. This is my x prime, y prime. We are aware that we have a b x prime over here, right? And then we will have a, hold on. So if this is, we are going to have our b y prime, okay? And then on the other side, we know that these are on a set of rollers, right? So we are also aware that we are going to have horizontally, we are going to have a b, not b, a, okay, x prime. Sorry, ay prime, not x prime. Okay. This is just to sketch the free body diagram. We don't have ax prime. Ax prime is equal to 0 because there's no resistance force. It's on a roller. Okay. So now, once we have this, right, we can now immediately put this in a horizontal component now. So we are now going to rotate the structure where this is x, this is y, this is rotation about z. So what we are doing now is from here, right, we rotate the structure horizontally now. So I'm going to sketch a structure horizontally. Hold on. So I'm not going to draw the edges. I'm just going to draw straight lines. Okay. So now this looks like this. Six, two. Okay. So we know that we have our GY move at 4.5 times 10 to the power 3, right? We also know that we have a GX in this direction, right? And our GX is sitting at 7.794. So this is our GX. So now we want to now know our reaction at point A and point B now. And we know that point A, we are now going to have a AY. And point B, we are going to have a BY. And if we were to look at point B, there's a reaction, there's an x-axis reaction over here, right? So this is going to take our BX. Okay, so at point A is still our roller. At point B is our P. So these two diagrams, the one on the left and the one on the right, it's equivalent. Okay, it's equivalent. So now we all we have to do now is to find AY, okay, and BY. So by looking at geometries, I'm going to draw down this geometry. Over here to here, this is 60 millimeters. And then over here to here is also 60 millimeters, right? So from here, we have positive that's going up. Summation of forces in the y direction is equal to 0. So we have AY plus by BY minus by 4.5 times 10 to the power 3 will be equal to 0. Okay, hold on. Let me put in the other mode so I can write thicker. So we have positive that's going up. Summation about forces in the y direction is equal to 0. So you have AY plus by BY minus by 4.5 times 10 to the power 3 is equal to 0. And then we will say note that AY is equal to BY. Why is that? Because the load is applied exactly at the center. We have 60 millimeters from AY to GY and 60 millimeters from GY to BY. So that's why AY is going to be BY. So therefore, 2AY is equal to 4.5 times 10 to the power 3, right? So you have AY, which is equal to BY, and this is equal to 4.5 divided by 2, 2.250 times 10 to the power 3 Newton. Okay. Then we do summation about forces in the x